Hi Year 9 students, I'm Norman Wildberger. Today we're going to start learning about scientific notation, which builds on our understanding of the index laws that we've been talking about in our last few videos. So what is scientific notation? Well, it's an alternative way of writing numbers, which is especially suited for very large or very small numbers. It's extensively used in the sciences, as the term suggests. So physicists, chemists, biologists, engineers will use scientific notation. It's a very convenient way of writing down a number in such a way that you can pretty quickly get a sense of how big or how small it is. Okay, so let's have a look at some examples of scientific notation to give you an idea of what's involved. All right, so let's have a look at these four rather big numbers. The first one is this one here, which we read, well, first of all, we have to figure out where we are. So this is ones, tens, hundreds. These are the thousands. These are the millions. That's the billions. So this is 4,500,000,000. 4,500,000,000. And now notice this alternate way of writing it as 4.5 times 10 to the 9. This is scientific notation for this number. And I remind you that 10 to the 9 is 10 times 10 times 10, altogether 9 tens multiplied together. And that's a number that starts with a 1 and then it has 9 zeros. Okay. Of course, that's also a billion. 10 to the 9 is a billion. So this is 4.5 billion. That's another way of saying what this is. Here's another number that looks a little bit like it, but it's actually quite different. This one is 4,500,000, which in scientific notation is 4.5 times 10 to the 6. 10 to the 6 is a 1 followed by 6 zeros, which is a million. Here's another number in scientific notation, 9.460528 times 10 to the 12. 10 to the 12 is, it's a trillion. So this is roughly 9 trillion. If I actually had to read it, I would say it's 9,460,520,400,000. That's what that number is. And here's an even bigger number, which is a 1 followed by 18 zeros. So in scientific notation, that's 1 times 10 to the 18. Now, where have I gotten these four numbers from? So these four numbers are, in some order, how big a light year is in kilometers. So you all know that light travels pretty fast. It travels very fast. It takes 8 minutes for a photon of light to get from the sun to the earth, approximately. And a light year is how far a photon of light goes in 1 year. So if you let a photon go for a whole year and you measure it, well, that's a certain number of kilometers, quite a large number of kilometers, and it's one of these four numbers. One of the other numbers is an estimate for the number of insects on planet Earth. Another one is an estimate of the age of the Earth in years. And the other one is the population of Sydney round about now. So I'll give it to you a little challenge to try to figure out, just looking at these four numbers, which of these four numbers corresponds to which of these descriptions. See if you can figure it out. This is part of this story here, that we're studying scientific notation, but we're also getting a sense, or trying to develop a sense, for really big numbers and the relative sizes of really big numbers. We don't want to just say, oh, that's really big, or that's really, really, really big. We want to be able to be a little bit more precise, a little bit more quantitative about how big things are. and how small things are. Okay, so let's have a look at some small numbers. Okay, let's have a look at this number here, 0.04267. And because we're a little bit less familiar with decimals when we're talking about the digits to the right of the decimal point than to the left. To the left, we're pretty familiar because that's sort of the normal numbers. But something like this, we are a little bit less familiar. So let me remind you what these various digits mean. The place right to the right of the decimal represents the 1/10 unit. Okay. To the left of the decimal, we have the ones and the tens and the hundreds and the thousands, as usual, marching off to the right, getting bigger and bigger. But to the right of the decimal, that represents the number of 1/10 in our number. And then the next represents the number of 1/100ths. The next 1/1000ths. The next 1/10,000ths. 100,000ths. So this is a number which is roughly 4/100ths big. So it's a pretty small number, 4/100ths. Take one, if that's one, then that's 100th, and 4 of those will be pretty close to this. There's a little bit more than 4/100ths because there's a few thousands thrown in and a few 10,000ths and 100,000ths too. So this is the standard way of writing this number, and here is the scientific notation way of writing that same number. 4.267 times 10 to the minus 2. The same digits are occurring here, but there's a decimal point in exactly this spot, right after the first digit. That was exactly the same kind of thing that happened on the previous page. We always had one digit and then a decimal point, and then some other digits if necessary. But here the exponent of 10 is a negative number. We're multiplying by 10 to the minus 2, which is 1/10 squared, or 1/100th. So we have to use negative exponents when we're describing very small numbers. But we're used to that because we have studied our index laws. We're comfortable with 10 to a negative power. Here's a much smaller number. 0.000000008. This is a very, very, very small number. Every time we move right, we're dividing by 10. So this is the 1/10ths, this is the 100ths, 1,000ths, 10,000s, 100,000s, 1 millions, 10 millions, 100 millions. This is 8 1/1000ths. That's what that number is. In scientific notation, 8 times 10 to the minus 9. Remind you, 10 to the 9 was a billion. So 10 to the minus 9 is 1/1,billion. It's a billionth of whatever unit we're talking about. This is a very small number. 0.005 is not so small, still small, but not anywhere near as small as that thing. And that's 5 times 10 to the minus 3. And this one, 0.0001. So this one's smaller than this one. It's a lot smaller than this one, but nowhere near as small as this one. It's 1 times 10 to the minus 4. So these are all examples of scientific notation kind of expressions for numbers. And in fact, these numbers come from real life in some sense. So one of them is the length of a red ant. And another one is the thickness of a cell. Remember we talked about how many cells, that we have many, many billions of cells in our body. So if you take any one of those little cells, it has a sort of a cell wall, and how the thickness of the cell wall is one of these numbers. The width of a golf ball is another one. You know, golf ball, how wide is it? And another one is the width of a human hair. Take a single hair and try to measure how wide it is. It's one of those numbers. And I again challenge you to try to figure out which is which. Alright, so obviously we are going to be using powers of 10 a lot with scientific notation, because that's the common feature of all the examples. Very big numbers have powers of 10 to a big positive exponent. Very small numbers are represented by powers of 10 with negative exponents. So let me just remind you that 1,000 is 10 cubed. And that means 10 times 10 times 10. And that the 3 here corresponds to the number of zeros there. And I hope you all remember that 1 million is 10 to the 6. There's a million with 6 zeros, represented by 10 to the 6. 10 to the 9 is a billion. We've already talked about that today. And here is 10 to the 12th, which is 1 trillion. One advantage in this kind of power notation for powers of 10 is that there's less room for ambiguity or confusion with terminology. Because it turns out that, for example, the term billion is not uniformly used across the world. All right, so for us, a billion is 1,000 times a million. So if you take a million and you multiply it by 1,000, you get a billion. But there are places, I think in Europe, where a billion means something different. It means a million millions. What we're calling a trillion. All right, so there's a bit of possibility of confusion here. And if you're watching from one of these countries where you use billion in a different way, okay, I'm sorry. But you can see that if we work with this index notation, then there's no possible ambiguity. 10 to the 9 is very precise. We know exactly what we're talking about. There's a 1 followed by exactly 9 zeros. And of course, along with these positive powers of 10, we're also going to be needing, like here, negative powers of 10. And I remind you that if we have 10 to the minus 3, what that means is 1 over 10 cubed. 10 cubed is 1,000, so that's 1 over 1,000. 10 to the minus 9 is 1 over a billion. 10 to the minus 6 is 1 over a million. So what we're going to do today is to prepare ourselves for understanding scientific notation and the relative sizes of very big things and very small things. We are going to solidify our understanding of how powers of 10 work in conjunction with other numbers, especially when we're multiplying and dividing by powers of 10. We've talked a little bit about this, but I want to really solidify our understanding of this. Okay? Especially, I want to convince you that there's no need to use a calculator here when we're talking about multiplying or dividing by powers of 10. I strongly discourage use of calculators most of the time, unless the numbers are very big and cumbersome. Okay? But for most of the examples that we're going to be doing, part of the notebook, say on the right-hand side, a margin, some room to make some calculations is all what you really need. All right, so let's practice and start understanding powers of 10 and how multiplying and dividing by those things works. So let's start with the familiar situation that I'm hoping you're already very familiar with, multiplying a number by 10. Okay. So when you multiply a number by 10, that adds a 0 to the right of the number. Or if it's a decimal number, it moves the decimal point over 1 to the right, 1 position to the right. Let me illustrate that, so make sure you absolutely are comfortable with this. 13 times 10. So if we want to multiply 13 times 10, it is very easy. Under no circumstances should we use a calculator. Right. To multiply 13 by 10, you just add a 0. The 3 ones become 3 tens. The 1 10 becomes 100. The effect is that all the digits move over 1 to the left, and there's a new 0 in the ones place. Another example, 206 times 10 is 2060. We're adding a 0. That's how you multiply by 10 for a regular number. Now what happens if you have a decimal number like 1.2? If you multiply 1.2 times 10, this is 12. In terms of the decimal point, what's happened is that it's moved over 1 to the right. So it's actually there. When we write 12, that's the same as 12.0 if you want, but the 0 doesn't have any effect. But we don't write the point 0 all the time. Sometimes we do, but we don't generally write it in ordinary arithmetic because it's unnecessary. We all know that there's a sort of a hidden decimal point there, that the ones place starts at the rightmost end of the number. All right, so this moving the decimal over, let's have another example of it. It's also happening here with a bit bigger number, 4.897. If we multiply by 10, the decimal place here moves over to the right to give us 48.97. And I hope that makes sense to you, right? If you have 4.8 and you multiply by 10, well, 4.8 is somewhere between 4 and 5, so you multiply by 10, you should be somewhere between 40 and 50. That makes sense. It's roughly the right size. And you might say, how does this description correspond to this other description of adding a 0? Well, in fact, it's really a lot the same, because if you think about 13 as a 13 with a decimal point to the right, just sitting there beside the 3, then what's happened is when we've multiplied by 10, we've gotten 130, where the decimal point is now over sitting to the right of the 0. So the decimal point has really moved from being here to being here. So it's really the same rule, it's just that there isn't a decimal point here that we're writing visibly to make it clear that it's really the same rule. All right, what about dividing a number by 10? Well, that's the reverse of multiplying by 10. And dividing by 10 is the same as multiplying by 1/10. Those are the same. And what does that do to a number? Well, it subtracts a 0 to the right, or it moves the decimal point over 1 to the left. So for example, 450 divided by 10 is 45. We just remove that 0, the 0 on the right-hand side. That's what dividing by 10 does. Multiplying by 10 takes 45 to 450. Dividing by 10 takes 450 to 45. How about a bigger number, 32,400? If we divide that by 10, what happens? Well, we have to lop off that 0 at the end. If we lop that off, then we get 3240. And if we write it in the usual way, that's 3,240. Sometimes there's no 0 to lop off. For example, 78. So how do we divide 78 by 10? Well, we think about the decimal place. The decimal point here is right beside the 8, to the right of the 8. Dividing by 10 moves the decimal place over 1 to the left. 7.8. If we multiply this by 10, the decimal place would move in that direction. We would get 78. They're inverse operations. 45.63 divided by 10 is 4.563. The decimal place moves over 1 to the left. And you can check in your mind, right? If you're dividing by 10, you should be getting a smaller number. You don't want to be getting 456.3. That's a lot bigger than 45. So you should be aware of the rough sizes of things just to check that what you're doing sounds reasonable. If we're dividing by 10, we should get a smaller number. 4.5 is smaller than 45. It's in the right direction. So the point is that dividing by 10 is very simple, just like multiplying by 10 is very simple. But I want to also show you this equivalent way of thinking about dividing by 10, of multiplying by 1/10. Okay? It's important to understand that those two things are the same. Let's have a look at some examples of thinking about it that way. All right, so here's some examples. 570 times 1/10. Multiplying by 1/10 is the same as dividing by 10. In this case, there's a 0 to the right of our number, and so dividing by 10 is very simple. We just remove that 0 and get 57. So here's another way of expressing division by 10. When we write a number and we write a bar and put the 10 in the denominator. So 6,300 over 10 is another way of saying 6,300 divided by 10. This number happens to have a 0 at the end, and so dividing by 10 is particularly simple. We just lop off one of those zeros and get 630. If we're multiplying by 1/10, we can multiply at the back or multiply at the front. It doesn't make any difference. 3 times 4 is the same as 4 times 3. That's the commutative law. So 1/10 times 49 is exactly the same kind of story. We're dividing by 10 essentially. Okay, here there's no 0 at the end. So what do? We take the decimal point, which is there, even though it's not shown, and we move it over 1 to the left to get 4.9. Is that the same thing that we were really doing over here? It's the same thing we were really doing over here. The decimal point that was over here, which wasn't written, was right there beside the 0, to the right of the 0. If we move it over 1 to the left, we get 57.0, which is 57. So the effect of that is just to make that last 0 negligible because it's on the right-hand side of the decimal now. It doesn't count. So the same thing here. If we think about the decimal point as being currently here, when we divide by 10, the decimal place moves over there, and we get 630.0, which is the same as 630. It's really the same rule, but when there's no decimal point, we're just essentially lopping off a 0. So here's another way of saying the same thing. 2.3 divided by 10, or 2.3 over 10. Same thing. The decimal point moves 1 to the left to give us 0.23. And finally, this interesting example, 0.778 divided by 10. Here the decimal point is already on the left-hand side. How do we move it over 1? There doesn't seem to be any space. Well, what we do is we just imagine a 0 here as a placeholder. Well, the point of the zeros in the Hindu-Arabic system is to act as placeholders. So if we think of a 0 as being there, then we do have room for the decimal point to move over. It can just move in front of the 0, giving us 0.0778. So these are different ways of thinking about dividing by 10. So we have dividing by 10 is really the same as multiplying by 1 over 10. And let me just point out that there's a third way of thinking about what dividing by 10 is. That it's taking 10% of a number. Okay, we're going to talk more about percentages later on in this course, but I hope you're at least somewhat familiar with percentages. I hope you all remember that 10% means 10%. Cent is a kind of Latin for 100. So 10% means 10 out of 100. 10% is 10 over 100, which is the same as 1/10. So 10% of, say, 570 is 57. It's 1/10 of 57. That's another way of saying this. 10% of 2.3, that's another way of saying this. We're taking 1/10 of 2.3, which is 0.23. All right, so multiplying by 10, dividing by 10. Okay, absolutely fundamental arithmetical operations that I want you to understand what's going on. And I want you to be able to smoothly multiply and divide by 10, whether we're thinking about it as being multiplying by 1/10, or whether we're thinking about it as being with a division sign with a 10, or even if we're talking about 10% of a number. All right, so we understand multiplying and dividing by 10. Let's go up a step and just make sure we understand about multiplying and dividing by 100. Okay, multiplying and dividing by 100. Let's start with multiplying, which is always simpler. So multiplying a number by 100. How do you do it? What does it do? It adds 2 zeros to the right of the number. Or, for a decimal, it moves the decimal place over 2 to the right. For example, 5 times 100 is 500. What we're doing is we're taking the 5 and we're adding 2 zeros to the right. And one way of thinking about that is multiplying by 100 is multiplying by 10 and then multiplying by 10 again. Because 100 is 10 times 10. So if you're multiplying something by 100, one way of thinking about it is first you multiply by 10 and then you multiply by 10 again. Since we know how to multiply by 10, it's adding a 0. If we multiply by 10 and then multiply by 10 again, well, the effect is to multiply by 100, which is adding 2 zeros. Another example, 137 times 100, we just add 2 zeros to get 13,700. How about 4.21 times 100? Well, now it's a decimal number, so it's not a question of adding zeros. Adding zeros wouldn't do anything to a decimal number like this, because 4.2100 is exactly the same as 4.21. If we have a decimal number, we have to move the decimal. That takes priority. That's the essential rule, if you like. So what happens to the decimal? Well, it moves over to the right. But it moves over 2 places, because we're multiplying by 100. If we multiply by 10, it moves over 1 place. So if we multiply by 100, it moves over 1 and then another 1, for a total of 2. So we get 421. The decimal point has moved from here to there, and once it's there, we don't need to write it down anymore. We just write 421. 8.6 times 100. Okay, have a look here now. This decimal point, if we multiply by 10, we get 86. And if we multiply that by 10 again, we're going to have 860. Again, it's a case of having to think about an extra 0 in a place, so that we have room to move our decimal point over. If we need to move this decimal point over 2 places, well, we can do it 1, no problem. But if we want to move it 1 more, we have to add a 0 to the right to give the decimal point some place to go. So 8.6 is the same as 8.60. And if we think of it as 8.60, then it becomes easier to see what happens. It's just we get the decimal place moving over 2, and we get 860. Here's an example of a smaller number multiplied by 100. So we have 0.00109. This is a rather small number. It's roughly 1,000th, because this is in the 1,000th place. It's a little bit more than 1,000, because there's also something in the 100,000th place. How do we multiply by 100? We move the decimal place over 2 places to the right, right to there. And once it's there, it's 0.109. We can ignore the zeros that are to the right of the decimal point if there's nothing in front of them. So we get 0.109. And let's point out that if required, we need to add zeros to the right of a decimal number to give room for the decimal point to be moved, as in this example here. That's multiplying by 100, which is really the effect of multiplying by 10 twice. Multiplying by 10 and then multiplying by 10. So that's multiplying by 100. What about dividing by 100? Well, it's kind of the reverse. It's kind of undoing the multiplication. So dividing a number by 100 subtracts or removes 2 zeros from the end, if there are 2 zeros at the end. And otherwise it moves the decimal point over 2 to the left. The second description is really the more fundamental one. It's really what happens to the decimal point that's really the important thing. So the first example, 900 divided by 100. In this case, there are a couple of zeros at the end of the number. If we divide by 100, we get 9. The effect is to remove those 2 zeros at the end. We can also write the division as something over 100. So if we divide 600 by 100, we can also write that as 600 over 100. And the effect is to remove the 2 zeros at the end to give us 6. A bigger number, 456,000 divided by 100. The effect is to remove the last 2 zeros, and then we get 4560, or 4,560. 123 divided by 100. In this case, there are no 2 zeros at the end. We have to think about what happens to the decimal point. Okay, we're going to get a decimal number. Right now, the decimal is sitting right there to the right of the 3. If we divide by 100, it moves over 2 places to the left to give us 1.23. Hope that makes sense to you. You have 123 divided by 100, you're going to get 1 and a little bit more. Make sense? 123 divided by 100, 1.23. 2.3 is almost like a quarter, isn't it? Because 2.5 is a quarter. So that'd be 1 1/4, roughly. How about 67 divided by 100? Now we're using this notation for division, which is also acceptable. Well, what still happens is the decimal place moves over to 1, 2. In order to give it a place to move over, we have to add a 0 to the left. That gives us a place for the decimal point to move over to. And 0.808 divided by 100. Here the decimal point is there. We're going to have to add 2 zeros on the left to give this decimal place somewhere to move to. So we get 0.00808. Dividing by 100 makes the number smaller. Going from here to here, the number has gotten smaller because instead of having 8 tenths, we now have 8 1,000ths. So this is a much smaller number than that one. Alright, so let's just note that dividing by 100 is the same as multiplying by 1 over 100. And in terms of percentages, that's the same as taking 1% of a number. Right. So dividing by 100 is actually quite important thing, and that's why I'm doing it separately here, because it's the same as taking 1% of a number. 1% means 1 per cent, 1 per 100, 1 over 100. So what's 1% of 900? It's 9. What's 1% of 123? It's 1.23. What's 1% of 0.808? It is 0.00808. Taking 1% of something is the same as dividing it by 100. Or the same as multiplying it by 1 over 100. Right? Percentages are going to be playing a reasonably important part of this Year 9 course. So we're going to be coming back to percentages and talking more about them later. But it's probably a good idea for you to connect 1% in your mind with the fraction 1 over 100, and to connect 10% with the fraction 1 over 10. Multiplying by 1/10, dividing by 10, taking 10% are all the same thing. And dividing by 100, multiplying by 1 over 100, taking 1%, they're also the same things. When we're working with scientific notation, we're going to be working with powers of 10, often much bigger than 10 and 100. So we want to understand how these rules that we've talked about for multiplying, dividing by 10 and 100 extend to higher powers of 10s. So let's think about multiplying and dividing by powers of 10 more generally. The same rules apply. Let's have a look at multiplying by 10 to the 4th, for example. If we're multiplying a number by 10 to the 4th, what happens? First of all, 10 to the 4th is what exactly? It's 1 with 4 zeros, which is 10,000. It's 10 times 10 times 10 times 10. That's 10,000. If we multiply by 10 to the 4th, or 10,000, what happens? Well, it adds 4 zeros to the right of a number. 4 zeros. Or in terms of the decimal point, the decimal point moves over 4 to the right. 4 because we're multiplying by 10 to the 4. For example, 3 times 10 to the 4. One way of thinking about that is it's 3 times 10 times 10 times 10 times 10, because this is 10 to the 4. So in your mind you can think that we're multiplying by 10 4 times. Multiply by 10, multiply by 10, multiply by 10, multiply by 10. Each time we're adding a 0. So we're adding 4 zeros to the 3 and getting 30,000. Which of course makes sense because we've said 10 to the 4th is 10,000. So 3 times 10,000, yes, that's 30,000. That makes sense. Something pretty close to that. Let's have a look at 3.1 times 10 to the 4. All right, 3.1 isn't that different from 3, just a little bit more. What's that going to be? Well, we have to multiply by 10 to the 4th. We have to move the decimal place over 4 places. We're going to get 31,000. And you can think of the decimal place as starting here. And then we move it over once to get 31. Move it over twice to get 310. Move it over another place to get 3,100. And then fourth to get 31,000. So we have to think about, there's a succession of zeros after the 1, which are there if we want to use them, but generally they don't have any effect. But when we're multiplying by, say, something like 10 to the 4th, then it's very convenient to have them there because they end up playing a role in the product. How about 47.5462 times 10 to the 4th? There's the decimal point. We're multiplying by 10 to the 4th, so the decimal point moves over 4 places. 1, 2, 3, 4. So we get 475462. The decimal point would be there, so we don't really need to put it in because it's just then 475,462. How about 0.06215 times 10 to the 4th? There's a decimal point. Move it over 4. 1, 2, 3, 4. We get 621.5. Okay. So it's the same kind of business as multiplying by 10, multiplying by 100. It's just that it's the exponent of the 10 which determines either how many zeros you add if you're multiplying by a natural number like this, or how many places the decimal point moves over if we're multiplying by a decimal number. And what about dividing by something like 10 to the fourth? Well, it's the opposite of multiplying. So this removes 4 zeros from the right of a number. If our number happened to end in 4 zeros, we would remove 4 zeros. In terms of the decimal expansion, which is more general, it moves the decimal point over 4 to the left. Moving the decimal point over to the left makes the number smaller. So for example, 30,000 divided by 10 to the fourth. Here there are 4 zeros to the right. When if we divide by 10 to the fourth, we remove those 4 zeros and we get 3. You can see that is the opposite of what we did with the multiplication. Similarly, 31,000 over 10 to the fourth means exactly the same thing as this. We're dividing by 10 to the fourth. Generally, we like to think about division a little bit more using this notation rather than this notation in high school. It works a little bit more smoothly with algebra if we think about division this way. Okay, the effect is to remove 4 zeros. Well, there are no 4 zeros here. There's 3 zeros, so we would rather think in terms of what happens to the decimal point. Right now there's a decimal point over there, even though you don't see it. Okay, but it's there. Moving it over to the left, 4 places. 1, 2, 3. That's effectively sort of gotten rid of 3 zeros. And now one more to give us 3.1. You say, why don't we get 3.1000? Yes, you can write it that way, but 3.1000 is the same as 3.1. Those extra zeros are not, in this case, telling you anything about the number. They're extraneous. They're not necessary. How about 89,174 divided by 10 to the 4 again? There's a decimal point there. Over 4, we get 8.9174. Or 56.02 divided by 10 to the 4, or over 10 to the 4. There's a decimal point. We need to move it over 4 to the left. Once, twice, now it's there. 3 times, 4 times. We add some more zeros over here as placeholders, giving the decimal point some place to go. Alright, so this kind of facility with multiplying and dividing by powers of 10, getting an appreciation for moving the decimal point around, becoming familiar with the idea of writing division this way or this way, same deal. Connection with percentages in the case of dividing by 10, dividing by 100. These are basic arithmetical skills. Okay? That's sort of the foundation for understanding scientific notation. Time for some practice. Alright, so some practice. And, very important, what are we going to do with our calculators while we're doing this practice? We're going to put them away. Unnecessary. Paper and pen, or paper and pencil, and eraser. It's the best combination. Evaluate 13 times 10, 4.5 times 10, 68 times 100, 0.3 times 10, 14.6 times 100, 0.039 times 100. Simple questions just involving multiplying by 10 and 100 to get us going. Second question, 40 divided by 10, 3,600 divided by 100, 51 over 100, 5,400 over 10, 0.28 over 10, 1.07 over 100, 10% of 49.3. Again, we're sticking here basically with division, just involving tens and hundreds. And for our third problem, graduating to bigger numbers. So 37 times 10 cubed, 4.905 times 10 to the fourth, 0.02 times 10 cubed, 59,000 divided by 10 cubed, 88.7 over 10 to the fourth, 1% of 379.2, and maybe a little bit tricky, 0.1% of 379.2. So not 1%, but 0.1%, which is 1/10 of 1%. All right, so I want you to start feeling comfortable with doing some arithmetic with bigger powers of 10. And I want you to keep an eye on the general sizes of things. After you make a calculation, have a look at it and say, does that sound reasonable? Right? For example, 4.905 times 10 to the fourth. If you end up getting 0.4, ask yourself, I'm starting with 4, I'm multiplying by 10 to the fourth, I'm getting 0.4. Wait a minute, how can that be? 4 is bigger than 0.4. I should be getting something that's a lot bigger than 4. So part of scientific notation is to develop an appreciation for the relative orders of magnitudes of things. That's actually kind of fun because there are lots of interesting big numbers in our world. There are lots of interesting, really small numbers in our world. So we're going to be developing some familiarity and confidence with working big and small numbers, and also some ability to be able to make ballpark assessments, to be able to appreciate when one number is bigger than another and roughly by how much. That's part of this story of developing scientific notation. So next time we are going to introduce scientific notation. We have set the groundwork today, and then we're going to have a look at it and look at some various examples. We're going to come back to the big numbers and the small numbers that I introduced in the first few slides today. So we're going to find out, what the width of a golf ball is and the age of the Earth, etc. All right, so I hope you'll join me for that. I'm Norman Wildberger. See you all next time.